Right, we live. I will first do Kruskov's algorithm and then we'll hand out the tests because otherwise nobody's going to listen to me. Okay, so remember we are building a minimum spanning tree of a graph. What is a minimum spanning tree of a graph? It is a tree containing all the nodes and the edges and a set of edges connecting the nodes so that the sum of all the weights is the minimum and that I still have a tree, so I can't have cycles. Then we look at Prim's algorithm. Prim's algorithm has two versions, the lazy version and the eager version. Okay. So what we do with Prim's algorithm is we look at cuts of the graph and crossing edges. So we basically start with a node, which can be any node. We claimed yesterday, but I didn't prove it. We start with a node and then we make a cut. And the cut that we make is over the adjacency list of that node, right? And then we put that node in the tree and we look at all the links adjacent to this node, which one has the minimum weight. Yeah? So then we take that and we put it into the tree. And we continue in that manner, but we do it somewhat cleverly. We keep all the edges with their weights in a priority queue so that we can keep on deleting the minimum weight. Yes, so we can keep on deleting the minimum. As we progress through Prim's lazy algorithm, some of the edges become ineligible, onwettig, because if I were to choose that, even though it has the minimum, it would cause a cycle. Right? So some of the edges become ineligible. Then we did the time complexity analysis and we found that the priority queue was the bottleneck in the algorithm. Right? So I cannot get a better performance than that offered by the priority queue. And then we said, well, let's change Prim's algorithm so that I'm not dependent so heavily on the priority queue. And that is Prim's eager algorithm. And there we actually have a priority queue with one element in it. We keep on just putting the minimum, the edge with the minimum weight that is eligible, we keep. And we keep on choosing that one, right? So we remove, in a certain sense, we make sure that the time efficiency of the priority queue deleting the minimum is very efficient, okay? Which means that this algorithm is more efficient than the one based on the lazy approach with the priority queue. Okay. But that algorithm of Prim's is based on the nodes. I select a node, I make a cut. I add another node, I make a cut according to that node. What we are looking at edges. So what Kruskal says is let's look at the edges. And right from the start, give me all the edges in the graph. And I'm going to select the one with the minimum weight repeatedly. And then as I select them, I just make sure that I am building the correct tree. Okay, so it's, I don't know. Prim's algorithm to me is sort of very intuitive because you take a node, you make your cut, you take another node, you make your cut. But if you look at Kruskal's algorithm, you think, well, why didn't I think of that? That makes more sense. So let's look at the edges. This is my graph. and I select the edge with the minimum weight, 0.7. Do you remember it from, let's just look at the values there. I have all the edges. I have all the edges with their weights, right? So I select the edge with the minimum weight. That's it. And that is 0.7, so therefore I make 0.7 with the connection I put into my MST, minimum spanning tree. Then I look at the next one, the next edge, so that disappears. So the next edge that I can choose is 2,3 with weight 0.17. There it is, I select it. Okay, yeah. And then I want to look at 1.7, it's 0.19, I select it. Okay, and then 0.2. Okay, but now I must be very careful. 5.7 is apparently the next one. I can still do 5.7, but now I am going to run into cycles. 5.7 gives me 0.28. Yes, there I choose it. The next edge with minimum weight is 1.3. But if I were to choose 1.3, I would get a cycle. Yes, can you see that? There, I would have a cycle. And 1.5 would give me a cycle there. Yes, and so on and so forth. So all the edges that would cause cycles as I go down this set of edges, I cannot choose. So how do I search for cycles? Again, the same question we had yesterday. And then there was a suggestion, and I said you have to look at it yourselves to see whether that is true or not. How do I search for cycles? In general, to find cycles in a graph is an expensive operation. Yes? So in this case, how do I know that I would create a cycle? We go back to that very first assumption about trees, the one that says, if I have a tree and I connect two existing nodes in the tree, that creates a cycle. Remember, I drew the binary tree on the board. Yeah? So all we need to know is which nodes are in the tree already. And once I know which nodes are in the tree, I can mark them. Then I know that another edge connecting them would create a cycle. So that is actually very easy to test, because we are not looking at some general graph and say, whoa, go find me a cycle. We are simply saying, I have a tree. I'm building a tree. I must just make sure that I don't add an edge which goes from an existing node in a tree to another node in the tree. Yeah, as easy as that. And then you carry on. And I select the edges, and there we go. There's my minimum spanning tree. Whoa, whoa, not quite. There's the final one. Okay. So it somehow feels quite efficient, because with Prim we had to do lots of things. You had to make a cut, and then you had to build the priority queue, and then you had to make sure link edges are eligible and so on. It feels like more work. So let's see what the difference is. The time and memory complexity, Kruskal's algorithm uses space proportional to the number of edges. Well, that makes sense because I store the edges. Yes. And time proportional to E log E in the worst case to compute the MST. Right. So note that, of course, it makes sense because this is an algorithm which is edge-based. I simply look at the edges and do things with them. Yes? So my time and space complexity is fully dependent on the number of edges. Whereas with prim, let me find that. Prim in the end also comes to E log E in the worst case, yes, which is strange because I thought it would be something to do with the nodes, but here we go, the lazy version, space proportional to E, time proportional to E log E. And it comes from the priority queue because we put the edges into the priority queue. So the algorithm itself feels as if it's node-based, but if you look at the time complexity, because it's all based on the priority queue, and we simply put the edges in the priority queue, we get the same thing. Right? The eager version of prim, do they have it somewhere? Eager version of prim uses extra space. Aha, this is interesting. The eager version of prim uses extra space proportional to the number of nodes and time proportional to E log V. And now you have to think. If you think about it carefully, why does, if you compare these three algorithms, why is the eager version of prim, which is supposed to be an improvement on the lazy version, now suddenly it brings V into the scheme of things? Also, you shouldn't look blindly at that log. We tend to say, oh, whoopee, log, it's good. But note the playoff between E and V, yes? Because you know that you can have some graphs with a lot of edges and a few nodes, a more dense graph, or you can have a graph with a lot of nodes and a few edges. So yes, depending on the application, one of these algorithms can be better than the other. It depends on the input that you give to it. So it would be interesting for you to try and draw a graph of E log V as E and V changes, yes, and E log E, which is independent of V, and see, you know, what is that density formula? What is that ratio between E and V that would actually tell me that Prim's eager algorithm is better than Kruskal's? Yes? Try to get a feeling for it. It's just not just maths on a page, it's actually practical. Okay? I may bubble sort. I may bubble sort 10 items repeatedly. I may not bubble sort 10 million items repeatedly. Okay? So with the graph that you get, it depends on the context which algorithm is best. Okay? And that context is what is the density of the graph. So would it be possible to find some ratio of V over E or V to E that would tell you, look, now is the time to actually switch over to Prim's eager algorithm rather than do the very easy Kruskal algorithm? Okay. Does that make sense? Yes.
I just saw in Kruskal's algorithm they use unifying instead of log and right side of the algorithm. And it just seems more expensive, so why would you use unifying?
Actually, to tell the truth, I don't know. Let's have a look. Where are the, oh, I see. Okay. I'll tell you on Monday. You threw me now, I don't know. Please send me an email. Okay. I just did not prepare that. I'm very bad if I get an unprepared, something which I did not prepare and I get a question on it. But send me an email. Meneer Siljet, jy voorstel.
That's just with this checking out the cycles that are, this might be expensive, but if you take a Boolean array, and then if both nodes are true, then don't add the cycle. Only if one is false and one is true, then add the cycle.
It's not expensive. Yeah, yeah. No, that's fine. Yeah. More? Het jy nou al die e-pos gestuur? Have you sent that email? Because you're going to forget. Once you walk out of the class, you're going to forget. Yeah, send me the email. And I will talk about it on Monday, I promise. Okay, there we go. Are there any questions about the practice? No? Right, so 155,990. Ach, dis min genoeg van julle. Okay, you can come and get your tests. Smallest. Slightly larger student numbers.
I want to see how he did. Stop. But this is. This is open, huh?
Oh, meneer Thiessen. You know, okay, it's
No, 80.
that's pretty profitable. Okay, is that it?
Convenient. Isn't it? On Monday, do you have reports for the project?
Come again?
The reports for the project again.
So if there's anybody else who's still looking for their project reports and mark sheet, it's as we can as well. In no particular order, sorry. We'll have to scratch through it all.
One at a time.
Anybody else still looking for the test? Do you have your tests? Does anybody else want to take their roommate's test? If you know the student number.
Yeah,
Otherwise, I'll put the office as usual. I wonder if I can send the reports, since it's not alphabetical. Sorry, I'll get you some.
louder.
Nee man, ek het jou nog dit allemaal. Did you find yours now?
No.
I remember I did Mr. Masava. There we go. I meant yours. Right, so what I'm going to do is I'm going to send the project report Meneer Thesen, het jy nou nie jou voorblad gekry nie? Hy was daar. Ek het hier okay, maar jy het jou punt, nie? Maar ek het hom ons nou vir jou spas gegee.
Dat is ook merk. Dat is dus medium report. Dat is dus die so.
Ja.
Want dit is een tak van maar dit is die statistiek en de economies.
Okay, gee die report terug, dan sal ek krap op doen. Right, so what I'm going to do now is sort of quickly go through the test. I asked question one. I asked question one because I wanted you to really, you didn't do well in the first test on basically the same question, a slight variant of the question. So I wanted to ask it again, and most of you did much better. Although, as I said in the email, I will not give marks for. This algorithm is a lot faster than the other algorithm, okay? Because that doesn't tell me anything other than you sort of have this vague gut feeling that it should be the case specified. You are either scientists or you are into commerce, and with financial management and science both give me the creeps if you are vague, because either the nuclear reactor will leak. Yeah. True. Okay. Let's narrow it down to accountancy. When you're working on my bank account, I want you to be as specific as possible. Yes, true content. So be specific. A search in an ordered array will be log n or logarithmic if you want. If you want to be vague, keep it logarithmic without specifying exactly how much. Whereas in a linked list, even if it is ordered, of course, my search time is linear. N. Right, but most of you did fairly well there, so I was happy. Then question 2, would you use a linked list or an array for an application that does 10 to the 3 put operations and 10 to the 6 get operations? The answer would be array, because I do fewer get operations, put operations than get operations. So I want my searching to be more as efficient as possible. So I can use binary search there, and I would do that 10 to the 6 times. The linked list is constant for insertion, right? Because I can just put in at the end or in front. It's not linear for insertion. Whereas with the array, it would be expensive to put. Yes? So array with any reasonable explanation. If you got array there, but you gave a nonsensical reason, I did not give you a mark. Okay, question 3, almost all of you got it right. The running time of algorithms on binary search trees depend on the order in which the keys are inserted. For n keys, what is the maximum height and the minimum height? So the minimum height is log n if the tree is balanced. The maximum height is n if I get that degenerate linked list if I input the data in order or reverse order. Some of you got confused and say when n is 1, the minimum height of the tree is 1, but you were supposed to specify the height in terms of n, not for specific values of n. Question 4 was, any questions? Right? Question 4 was a beautiful one, I think. The answer, it's straight from the book, by the way. So if you did work through the questions and answers, you should have gotten this right. D is the answer, because if you try to follow that path, you will start with 2, and I'm looking for 5. 5 is bigger than 2, so I go the right-hand branch. Then I get a 7. 5 is less than 7. 3 is less than 5. But now I cannot get an 8. Because if you look at the way a binary tree is structured, that 8 is out of place. 2. If I get to 7 and then 3, I cannot get an 8 to the bottom of 3. The 8 must go to the right of 7. Yeah, so that is not possible, the way I search for 5 there. Yes. Define a 2-3 search tree, question 5. There is on my memo, it gives a formal definition straight from the book. I accept it if I understood your definition, okay? So it's not, I didn't expect this straight from the book definition, but you must be careful with definitions. You must stand back from the question and ask yourself, if I tell this to a first-year student, will they understand what I'm saying? So you cannot simply jot down the properties of a 2-3 tree. You must, you must give a definition that will make your grandmother understand what a 2-3 tree is. Good. My poor grandmother always gets the blame for everything. Maybe she's a professor in computer science. Then your grandfather. Okay. Right. 6 questions? No? Question 6, given the 2-3 search tree below, describe how to insert the key Z. Use both a verbal description and redraw the tree. Okay, some of you only drew the trees and then I subtracted marks. So to insert Z, clearly, I go down the right branch. Z is bigger than M, Z is bigger than R, so I have to insert Z somewhere near SX. So we create a temporary for node SXZ, and then because I now have a temporary for node, I have to change it into not being a for node because this is a 2-3 tree. So I take the middle element X and I bubble it up to my parent. So just the right-hand side of the tree, I will get M or PX. Yeah, what do we know? P on the left-hand side, SXZ. So X bubbles up to R. And then this thing is changed into the 2 node as well, because this is a 3 node. Yeah, there we go. Right, so that is your final answer. That's like straight from the book, I just changed the values. Okay, again, 7a, define a red-black search tree. In a definition, you cannot, like this, define a red-black search tree. You cannot tell me a red-black search tree is more efficient than a 2-3 search tree. That is a property. That is not what the thing is. Okay? Yeah, so this, incidentally, is a nice definition. A red-black search tree is a 2-3 search tree. where a black link represents a 2-node and a red link represents a 3-node. I can live with that. That tells me this student understood what it is. Okay. Right. Difficulty with 2-3 search trees. That's solved by the red-black search tree. Actually, it's something that came up in class. I don't think it's necessarily in the book. We never gave an implementation for 2-3 search trees because it's just too tricky. So the answer, clear and simple, was 2-3 search trees as they are there are difficult to implement. Why? Because you have to have 2 different types of nodes in one structure. Yeah. So the red-black search tree is basically just an implementation of a 2-3 tree with only 2 nodes. So we can use all the binary tree implementations if we add this color to the thing. So it's not a deep question. Question 8 was bad. That was the draw the red-black search tree when you insert the path. So it was a very long question. I actually redid it myself. I looked at the memo, which I drew up in December last year. And then a lot of people gave different answers. So I sat down and I looked at the book and I redraw the thing painfully correctly. And it took me a couple of minutes to do that, even with the book open next to me. So this was a very long question in relation to the marks you got for the question. But I was very happy that a large percentage of the class actually got this. So I was impressed with that, okay? Which means you can do this, which is cool. Okay. Do you want the answer? It's P. Let's just draw it. Because it's not on the official memo, I was lazy and did not draw the picture in like that. This represents red. 2 equal signs next to each other. I may do that. Yeah, I don't know, this is wrong. You didn't even yell at me. From L. See, I can't draw it this way. Okay, let's do it. Yeah, let's redraw. L, which gets an M, and this goes to, this goes to C, and C goes to H. A, I have to keep my height, right? And this goes to Y, this goes to X, this goes to S on the same level as M, but this. Actually, a large percentage of the class got that right, which is cool. Okay, question. It's just that it's not always clear. If you could have used a green pen. Question 9. Okay, this was a somewhat "are you awake" question. And I explicitly asked Lodewijk to point out the percentage M on the next line in case you miss it. Did he? Yes, he did. Okay. So math apps can return a negative number. Yeah. And that was the thing. Okay, question 10 drove me to tears because a noticeable percentage of the class did not know what linear means. Ach nee man. Or you were just in a real hurry when you got there. Which of the following scenarios leads to expected linear running time for a random search hit in a linear probing hash table? Now, what's a linear probing hash table? This is where I have a hash table. I'm hashing to a certain index. Yes, this is the index. And then with linear probing, if I get a collision, I make a linked list. The thing about a hash table, what is the time complexity for a search hit? Well, if there's no collision, it is 1, because I calculate the index, I go there, and that was what I was looking for. So that is 1, that is constant, that is not linear. Right? So the only way, so clearly it has to do with the collisions, because if I don't have a collision, it's not linear. Right? So what happens with collisions in a linear probing table? A linear probing table say, if I get a collision, use the next element. If I still don't have space open, take the next element in the table, and so on. So with n keys, the only way I can have a linear time complexity for a search hit is if I have to look through all of them, which means that my cluster is almost the size of the array itself. Yes? Because I have to search through the whole array. That is linear. And therefore, the answer is A. Yeah? All the keys hash to the same index. So I insert the first one, then I get whatever, one somewhere. Take this one. I hash, I get this answer, I insert. I hash again, I get the same answer, I have to insert there, and so on. So my cluster is linear in size in terms of the number of keys. Okay, question 11. I wonder if I have to put hashing into the next test as well, because it seems to me that was the last part of the work and you were not, as a group, so happy with hashing. R versus M. So you have a modular hashing scheme for string keys with R is 256 and M is 255. The ratio of R to M says how many keys do I have versus the space in my table. So since the ratio there is almost 1, you'll get a lot of collisions. Not a good idea. So some people answered, you must have prime numbers. And my question to that is, if I choose R equals 17 and M equals 17, I will still get a lot of collisions. So it's not, prime numbers in general is a good idea, but the ratio between R and M, that alpha value that is given in the textbook, cannot be almost equal to 1. That was the whole problem. Okay, 12. I think there were the proof. 1 or 2 of you got confused with another proof. But all in all, those of you who did learn this got this. And then the bonus question, which I never gave the answer and refused to give the answer still, that you had to look up on Google. Okay. Either the time you were a bit pressed for time or you just didn't learn the proofs. Which one was it? Because I tended to get empty last pages. But the question is that because you chose not to spot the proofs or because you ran out of time?
I did struggle. I rushed in my proofs because we had like 3 minutes left.
Okay. So how many of you felt that you were quite rushed? Okay, so that was a general. I sort of think that question 8 was the culprit, because I spent a considerable amount of time.
There was 2 drawing questions, so that takes a lot of time.
No, what the other drawing question was like.
No, it's not writing. You have to actually spend time analytically.
Oh, okay.
It takes a lot of time.
Okay. I think there's less drawing in the next test. Okay, all in all, your feelings about the test, was it fair? Are you happy with your marks? I know this is slap bang right in the middle of all your other tests. So normally with chapter 3, because it's the most difficult chapter in the book anyway, the test on chapter 3 is the most difficult, and it's slap bang in the middle of your sort of normal test period. It happens that this is where the average is not that good. The class average was 53%. So my curve should have been here, and it's sort of doing that. And I love this part. There were a couple of people whom I won't embarrass, but who got, who got 88 and 90 and 77 and so on. So there are enough of you to make me happy. It's about 10% of the class did very well. Some of you did less well than last time, but I think still, the average is not that bad given the circumstances. Are you happy? Were you like phoning your grandmother and complaining about this horrible CS test or not? Yes. Jy was ongelukkig. Meditate. Okay, so the time was an issue. Okay. I do have to counter the extremely good marks you got for your project, right? So at the end of the course, I hate grading, right? Not the physical act of sitting down and giving marks, but that somebody can say, because I memorized this or I memorized that, or I don't understand this, I get a worse mark than somebody else. I hate failing people. But on the other hand, so I am in this system, but I do try not to disadvantage people too much because of the system. So at the end of the year, I do promise I take all your marks into account. I look at your general performance. Yeah, okay. You also know that out of the 5 theory tests, your sub-minimum only depends on the 4 best of them. Yeah, which is not for the cum laude candidates relevant, but anyway. Okay, any questions more on the test? Come and see me if you're unhappy. Otherwise, good luck for tomorrow. Yeah, if you really do bad, it sort of gives you this, you know, if I really did bad in one test, if only I did better in the other four, I could still do it.
Ja, nou ken jy.
Ek het vanaf gehoor, ons volgende toets is dit die eerste of tweede week se Vrydag vir die toets.
Ek weet nie, ek moet maar op die skedule staan.
Okay, maar dit is hy wat geskuif is nie.
Nee.